To determine the appropriate KVA rating for a main power transformer, you can use a formula that considers your peak KVA requirements, a contingency factor, and a load factor. The formula is KVA rating equals peak KVA requirements plus 20% contingency, all divided by the load factor. Let's break down each component of this formula. Firstly, peak KVA requirements refers to the maximum KVA demand of the load, including items such as three-phase motors, heat trace, and lighting. Accurately assessing this peak demand is critical for proper transformer sizing. Secondly, the 20% contingency is an additional buffer added to the peak KVA requirements. This accounts for potential future growth in your load or any unexpected increases in demand. It provides a safety margin to prevent the transformer from being overloaded. Thirdly, the load factor is a dimensionless factor that represents the average demand of the load over a given period. For example, if your equipment operates for 8 hours per day, you might use a load factor of 0.6. The load factor reflects how consistently the load draws power. To illustrate the calculation, let's consider an example. Suppose your peak KVA requirements are as follows: three-phase motors consume 100 kVA, heat trace requires 20 kVA, and lighting accounts for 10 kVA. Your total peak KVA requirements would be 100 kVA plus 20 kVA plus 10 kVA, which equals 130 kVA. Now, assuming a 20% contingency and a load factor of 0.6, we can calculate the KVA rating of the main power transformer. Using the formula, KVA rating equals 130 kVA plus 0.2 times 130 kVA, all divided by 0.6. This simplifies to 156 kVA divided by 0.6, which equals 260 kVA. Therefore, based on these assumptions, you would need a 260 kVA main power transformer from the utility company. This transformer size should adequately meet your peak KVA requirements, while also incorporating the contingency and accounting for the load factor. It is essential to carefully determine each of these factors to ensure accurate transformer sizing and reliable power delivery. The peak KVA requirements must be based on realistic load assessments. The contingency should reflect anticipated growth or potential demand increases. The load factor must accurately represent the average load demand over time. By using this formula and carefully considering these factors, you can determine the appropriate KVA rating for your main power transformer. This will help ensure reliable operation and prevent overloading the transformer. In electrical engineering, accurately sizing a transformer is paramount for efficient and safe power distribution. An undersized transformer will overheat and potentially fail, while an oversized transformer is an unnecessary expense. Therefore, a systematic approach to transformer sizing is crucial. Let's delve deeper into each of the components of the KVA rating formula, starting with peak KVA requirements. This represents the maximum apparent power, measured in KVA, that your facility or load will demand at any given time. It encompasses all electrical loads, including motors, lighting, heating, and any other equipment that draws power. To determine the peak KVA requirements accurately, you should perform a load analysis. This involves identifying all electrical loads, their individual KVA ratings, and their operating characteristics. For motors, consider the starting KVA, which is typically several times higher than the running KVA. For lighting, include all fixtures and their respective ballast KVA. For heating, account for the maximum heating load during peak demand periods. Once you have compiled a list of all electrical loads, you can estimate the peak KVA requirements. However, it is important to consider diversity factors. A diversity factor is a ratio that reflects the fact that not all loads will operate simultaneously at their maximum demand. For example, lighting loads may be low during daylight hours, or some motors may only operate intermittently. Applying appropriate diversity factors can reduce the overall peak KVA estimate, resulting in a more accurate transformer sizing. The 20% contingency factor provides a buffer for future load growth or unexpected increases in demand. It is a common practice to add this contingency to the peak KVA requirements to ensure that the transformer has sufficient capacity to handle potential future needs. The appropriate contingency factor may vary depending on the specific application and the anticipated growth rate. In some cases, a higher contingency factor may be warranted. The load factor is a critical parameter in determining the transformer KVA rating. It represents the ratio of the average load demand to the peak load demand over a specific period, typically a day or a month. A load factor of 1.0 indicates that the load operates at its peak demand continuously, while a load factor of 0.5 indicates that the average load is only half of the peak load. The load factor is used to account for the fact that most electrical loads do not operate at their peak demand continuously. By considering the load factor, you can avoid oversizing the transformer and reduce energy losses. The load factor can be determined by analyzing historical energy consumption data. If such data is not available, you can estimate the load factor based on the operating characteristics of the loads. For example, if the loads operate for 8 hours per day at a relatively constant demand, the load factor can be estimated as 8 hours divided by 24 hours, which equals 0.33. Once you have determined the peak KVA requirements, contingency factor, and load factor, you can use the formula to calculate the required transformer KVA rating. It is important to note that this is just an estimate, and the actual transformer size may need to be adjusted based on other factors, such as voltage regulation, transformer impedance, and available transformer sizes. In addition to the formula, there are other considerations that should be taken into account when selecting a transformer. Firstly, voltage regulation refers to the ability of the transformer to maintain a constant output voltage under varying load conditions. A transformer with poor voltage regulation will experience significant voltage drops under heavy loads, which can affect the performance of sensitive equipment. Secondly, transformer impedance is a measure of the transformer's resistance to the flow of alternating current. A transformer with high impedance will have higher voltage drops and losses, while a transformer with low impedance will have lower voltage drops and losses. Thirdly, the available transformer sizes are limited by manufacturers. You may need to select a transformer size that is slightly larger than the calculated KVA rating to ensure that it is readily available. Finally, it is essential to consult with a qualified electrical engineer to ensure that the transformer is properly sized and selected for your specific application. An electrical engineer can perform a detailed load analysis, consider all relevant factors, and recommend the most appropriate transformer for your needs. Understanding transformer nameplate data is also crucial for safe and efficient operation. The nameplate provides key information about the transformer's capabilities and limitations. Firstly, KVA rating indicates the transformer's maximum apparent power output. Secondly, voltage ratings specify the primary and secondary voltage levels. Thirdly, impedance is expressed as a percentage and affects voltage regulation and fault current. Fourthly, frequency indicates the operating frequency, typically 60 Hz in North America. Fifthly, winding configuration describes how the primary and secondary windings are connected, such as delta or Y. Sixthly, temperature rating indicates the maximum allowable operating temperature. Lastly, insulation class specifies the temperature withstand capability of the insulation materials. Regarding transformer connections, different configurations are used based on the application requirements. Firstly, delta-delta connections are commonly used for three-phase power distribution. Secondly, Y-Y connections are suitable for serving balanced three-phase loads. Thirdly, delta-Y connections provide a grounded neutral point on the secondary side. Fourthly, open delta connections can provide limited three-phase power with only 2 transformers. Transformer efficiency is a critical factor in minimizing energy losses and operating costs. Efficiency is the ratio of output power to input power, expressed as a percentage. High-efficiency transformers reduce heat generation and extend the transformer's lifespan. Energy-efficient transformers often have higher initial costs, but the long-term savings can be significant. Transformer maintenance is essential for ensuring reliable operation and prolonging the transformer's lifespan. Regular inspection should be performed to check for any signs of damage, overheating, or oil leaks. The transformer oil should be tested periodically to assess its dielectric strength and contamination levels. Bushings and connections should be inspected for corrosion or loose connections. Cooling fans and radiators should be cleaned to ensure proper cooling. In addition to routine maintenance, it is essential to implement proper protection measures for the transformer. Overcurrent protection devices such as fuses and circuit breakers should be installed to protect the transformer from overload and short-circuit conditions. Grounding is essential to ensure personnel safety and prevent damage from ground faults. Surge arresters should be installed to protect the transformer from voltage surges caused by lightning or switching operations. Transformer loading considerations are crucial for preventing overheating and premature failure. The transformer should not be loaded beyond its KVA rating. The ambient temperature should be considered, as higher temperatures reduce the transformer's capacity. Harmonics can increase transformer losses and cause overheating. Ventilation should be adequate to dissipate heat generated by the transformer. In summary, determining the appropriate KVA rating for a main power transformer involves a systematic approach that considers peak KVA requirements, a contingency factor, and a load factor. A detailed load analysis should be performed to accurately assess the peak KVA requirements. The contingency factor should reflect anticipated future growth or potential increases in demand. The load factor should accurately represent the average load demand over time. In addition to the formula, other factors, such as voltage regulation, transformer impedance, and available transformer sizes, should be considered. Consulting with a qualified electrical engineer is essential to ensure that the transformer is properly sized and selected for your specific application. Understanding transformer nameplate data, connections, efficiency, maintenance, and loading considerations are also crucial for safe and efficient operation. By following these guidelines, you can ensure that your main power transformer is properly sized and selected to provide reliable and efficient power to your facility.